Particle interactions, Feynman diagrams. So, as a recap, we have four fundamental forces: gravity, electromagnetism, the weak nuclear force and the strong nuclear force. Only charges feel the electromagnetic forces, so neutral particles like neutrons and neutrinos don't feel that force. Only hadrons feel the strong force, so hadrons are the particles that are made of quarks, so only particles made of quarks feel the strong force. All particles feel the weak force, and all particles feel gravity. Now, each force can be modelled as if the force is happening because it's making the particles exchange what's called a virtual particle between them. Some other names for the virtual exchange particle are the exchange boson or a gauge boson. All those names mean the same thing, that the force is making two particles swap a particle between them, and that's how they feel the force of each other. So the strong force, the exchange boson, is either the gluon or a particle called the pion, which is a meson. The electromagnetic force, the exchange boson, is a virtual photon. The weak force is going to be a W particle or a Z particle, and gravity is an unknown particle that we'll call the graviton. Now, in the 1940s, scientists were trying to make quantum mechanics even better, and so they developed what's called quantum field theory, which is that you imagine the entire universe is made of a quantum field, and each part of that field is a little quantum mechanical oscillator. Richard Feynman, one of the inventors of quantum field theory, realized that there was a lot of mathematics in quantum field theory, and that you could simplify how you do that maths by using diagrams to do some of the maths for you. Those diagrams are called Feynman diagrams. So a Feynman diagram is a pictorial representation of the maths that describe how particles in a quantum field are interacting. It's important to realise that a Feynman diagram is not a picture of what's literally happening with the particles. The lines in Feynman diagrams are not showing movement. Each line is just a shorthand for a bit of maths. So because it's maths and not just a diagram, there are strict rules about how a Feynman diagram has to be drawn, just like there are rules in how we do mathematical operations. So the Feynman rules are these. Rule number one is that the exchange particles, the exchange bosons, the virtual particles, are always represented by a wiggly line. Rule number two is real particles are represented by straight lines. Rule number three is that you draw whichever particles exist before the interaction at the bottom of the diagram. Right, remember that the arrows don't show movement, they show progression in time. So the arrows indicate going from past to future. They don't indicate going up and up to bottom to up or left to right. Right. The fourth rule is that baryons are always drawn on one side and leptons are drawn on the other side. And rule 5 is that the W gauge boson carries charge from one side of a diagram to the other in weak interactions. So the W minus particle is going to carry a charge of -1, and the W plus particle will carry a charge of +1. So here's an example. We've got a proton and another proton, and they interact through the electromagnetic force and they repel each other. So we always have to ask the same set of questions whenever we draw a Feynman diagram. What are the particles before the interaction? What are the particles after the interaction? And which force is it? So before, we've got two protons. Because they just push each other apart, after, we've still got two protons. We haven't made a new particle, we haven't got rid of a particle. Now, because it's protons and protons, it's going to be the electromagnetic interaction that's causing them to push apart. So for the electromagnetic interaction, the exchange boson is a virtual photon. So we can draw this diagram like this. We draw the lines representing the particles in time beforehand. So we've got a proton moving forward in time and another proton moving forward in time. They're on the bottom because on the bottom we draw the particles that we had before the interaction. Then they interact, and that's going to be always a wiggly line. This wiggly line is going to be a photon, so we have to label it as a photon. Then after they push each other apart by exchanging a photon, we have two protons moving forward in time after the interaction, so we draw that on the top of the diagram. So the Feynman diagram has this shape. It's going to have that shape for any electromagnetic interaction. So on the left-hand side, we've got two electrons on the bottom, left and right, interacting, and then two electrons afterwards. And on the right-hand side, we've got an electron and a proton attracting each other. Whether it's repulsion or attraction, the Feynman diagram looks the same. Remember, the arrows getting closer together or further apart does not represent the movement of the particles. It's maths in disguise. It's not a diagram of what the particles are actually doing in physical space. So another example we can use is beta minus decay. So remember, in beta minus decay, a neutron turns into a proton and gives off an electron and an antineutrino. So we ask the same questions again. We ask, what were the particles we had before? Answer, one neutron. What are the particles that we've got after? We have one proton, one electron, and one antineutrino. Because it's a particle decay and the particles change in type, it must be the weak interaction. The weak interaction is the one that makes particles change type. So because it's a weak interaction, the exchange boson is a W boson. So we draw the diagram like this. We draw the neutron. That's the only particle we had before, so that's the only arrow on the bottom. Then we draw the arrows above that represent the particles that we have after the interaction. So we have a proton, an electron, and an antineutrino. We're going to connect them by a wiggly line to represent the boson. And in this case, we need the W minus particle because the neutron has to give negative charge to the electron. So we draw an arrow on the wiggly line to show it going from left to right, and it's going to be a W minus particle. Beta plus decay is going to be the same thing, except that now we started with a proton, so we've got a proton on the bottom, and we have a neutron, a positron, and a neutrino on the other side. This time the key difference is going to be that we have a W plus particle as the virtual boson, because the proton has to give its plus charge to the positron for it to take it away. Electron capture is a process by which a proton captures an electron and absorbs it and turns into a neutron. And to conserve lepton number, it has to give off a neutrino. So before the interaction, we've got a proton and an electron. They interact and give us a neutron and a neutrino afterwards. Because a particle's change in type, it must be the weak interaction. So we have the W boson is exchanged between them, and here it's going to be the W plus particle because the electron has to lose its charge and turn into a neutrino. If you're confused about whether it's going to be a W plus particle or a W minus particle, what you can do is once you've drawn the diagram, just think about the leptons on the right hand side of the diagram. So ignore the left hand side of the diagram and go from top to bottom. On the bottom, we've got an electron with a charge of -1. At the top, we have a neutrino with a charge of 0. We have to go from a charge of -1 to a charge of 0. That means we have to add +1 charge to go from the electron to the neutrino. So that means that the exchange boson must be the plus W particle, not the minus W particle. Notice that electron capture and beta plus decay have totally different Feynman diagrams, even though they're very similar. So we've got the same 4 particles. We have a proton, a neutron, and either a positron and a neutrino, or an electron and a neutrino. But in the electron capture case, we have a proton and an electron before they interact. And in beta plus decay, we've got one particle, the proton. So remember, you have to draw the lines above or below the middle of the diagram, depending on whether they're things that were there before or after the interaction. Another example would be an electron-proton collision. So here we're going to have an electron that collides with a proton, and we're going to produce a neutron and a neutrino. And we could write that as either a W plus particle going from left to right, or a W minus particle going from right to left, right? So that, because that's the same exchange of charge. I would keep it simple and just have the particle, the exchange boson, always going from left to right, and just think about the right hand side of the diagram and the charges there. So in summary, there are these three types of Feynman diagram that are worth remembering. So there's the electromagnetic interaction, where you'll have two particles in and two particles out, and they'll swap a photon. You have a particle decay, where you'll have one particle in and three particles out. It will be the weak exchange boson, so you have a W boson, and you just need to decide whether it's the minus or the plus. And then you'll have particle absorptions, where you'll have two particles in and two particles out. Again, that will be the weak interaction because a particle changes type. And again, what you just have to decide is whether it's the W plus boson or the W minus boson.